here, Texas Southern. Not just the undergraduate, some stuff Dr. Nathan and I looked at as well. But in particular, we will discuss the discrete analogs of differential equations, constructing some nonlinear difference equations, iterative difference equation, I'll tell you, with maximum, and I'll tell you what that is, and maxilinear difference equations. Emphasis will be placed on solution behavior, including oscillatory behavior, periodic behavior, and other qualitative properties of solutions. Find the best discrete analog of, notice that's a differential equation, and A is a positive constant here. That was a problem. Describe the solution behavior of that x of n plus 1 equation. Notice it's second order. The way we get the order of a difference equation is look at the lowest subscript, take the highest subscript and subtract the lowest subscript, and that gives you the order. So that equation listed there is second order, because the highest subscript is n plus 1, the lowest one is n minus 1. So it's second order. Here we're looking at again, notice this is second order, and we're looking at a function f here, and when I say that the f has order 2, it means that f circle f, the f circle with itself is the identity function. Or order 3 means f circle f is the identity function. Okay, and so forth. Then this one is the what I call a maxilinear difference equation. It involves the maximum operator, and then you have linear pieces to it. Okay? Okay, so the discrete analog problem, if you look at this simple differential equation of order 4, if you solve it, you find out that the general solution is y equals c1 e to the t plus c2 e to the minus t. And so e to the t and e to the minus t, cosine t and sine t are all solutions to it. And notice e to the t is an unbounded solution as we go to infinity. E to the minus t goes to 0. Cosine t and sine t oscillate back and forth, right?
Mm-hmm.
Okay. So, part of mathematics is being able to generalize, right? So if you take instead of looking at y, what did I have there? Replace the coefficient of y with a to the 4th. Right? Oops. Okay. Yeah. Okay, so instead of using 1, just look at a to the 4th. Again, if you find the roots of the characteristic polynomial, you find that the general solution there is e to the at and e to the minus at and cosine at and sine at. And so it has basically the same properties, okay? But I'm trying to find a discrete analog of that, a different equation that behaves sort of the same way, with the solution behaves sort of the same way. Okay, now e to the at is what we call strongly increasing. It's like, e to the function is positive and all of its derivatives are positive, basically. E to the minus at is what we call strongly decreasing. It's positive, but its derivative is negative. Second derivative is positive. Derivatives alternate in sign. Cosine at and sine at are bounded solutions and oscillatory. So we say, well, I'm looking for a discrete analog, so let me go switch to a different equation. So suppose I look at u sub n plus 4 minus a to the 4th, u sub n equals 0. Well, you actually solve that by forming a characteristic equation and finding the roots. And a is it would be something like a m to the 4th minus a to the 4th equals 0. And when you solve for the a's here, you find out that 8 to the n would be a solution, minus 8 to the n would be a solution, A to the n cosine n power of 2, da da da, be the solution. So that turned out to be the general solution. That turned out to be the general solution. But if A is less than 1, now remember I'm assuming A is positive, but if A is less than 1, all those solutions tend to 0. Yeah, all tend to 0. If A is 1, all the solutions are periodic. Okay? If A is greater than 1, all the solutions are unbounded. So what can I conclude from that? Well, I conclude that E3 is not a very good discrete analog. Okay? E3 not a very good, because remember, we had that unbounded solution going up to infinity, we had one going to 0, and then we had those two oscillatory things. So this is not a very good analog. So then I said, okay, let's look at the delta 4 u sub n minus e to the 4th u sub n equals 0. Well, where A is positive, and we know that we're looking at the forward difference. Delta u sub n is u sub n plus 1 minus u sub n. Remember that the delta is the discrete math as the derivative is the continuous math. Works beautifully, beautiful stuff. But when A is 1, if A is 1, that equation up there, E4, turned out to no longer be order 4. Because that if A is 1, that u sub n term drops out. It becomes order 3. So I conclude, hey, E4 not very good discrete analog either. Because if A is 1, you don't even have a 4th order equation. Okay, so that won't work. Okay, so I remembered, I was still searching, but it turns out that 25 years before I started working on this, I had actually, I guess I had forgotten. I had actually looked for a discrete analog with the plus case, and I actually found one. And it had a subscript on the u sub n, it was n plus 2. So I said, oh, let me look at this one. Let me look at this one here. And so looked at that one, which I'm calling number 1 now, where A is a positive constant. If you assume that u sub n is t to the n, and plug all that into the stuff, you get this characteristic equation I call CE, characteristic equation, 4th degree, but it can be factored. See, it can be factored into 2 quadratics. Okay, so we get those 2 quadratics, right? Get those 2 quadratics. And so, if you find a T1 there, and a T2, okay, and then that for one of those quadratics, and then a T3 and a T4 from that other quadratic, so you get these 4 roots, okay? And now remember, we're going to look at t to the n, right? Well, it turns out if you take that T1, the first one we found, it turned out to be strongly increasing in the sense that it's positive. When you delta on u sub n, when you delta on that u sub n, it's positive. Delta 2 on it is positive. Delta 3 is, okay. So this, hey, this is like that E function, E to the AT function. The function is positive and all of its derivatives are positive. Here, the function is positive and all of its differences are positive. Cool. You look at the T2 one we found. It's positive, but the first difference turned out to be negative. Second difference was positive. Third difference negative. Okay, that's like e to the minus 18. Cool. Looking good here. All right. Now, it turns out though that the T3 and the T4 will be complex conjugates of each other when only when A is between 0 and 4. Okay. And it turned out if A equals 4, the roots, the T3 and T4 are actually repeated roots. And when A is greater than 4, the roots T3 and T4 are real and distinct. Okay. So we're in the ballpark now. So we notice that, so note that when A is between 0 and 4, the magnitude, the absolute value of the T3 and T4 is actually 1. And we do get a pair of solutions, what I call V sub n and W sub n, that oscillate, basically. And so those are bounded and oscillatory. This is looking good. This looks like we may have found something. So I do conclude that 1 is a good discrete analog of E2 when A is between what? The 0 and the 4. That's cool. That's all cool. Now when A equals 4, again, the T3 and T4 turn out to be minus 1, and from that we get some oscillatory solutions, one of them being bounded and one of them being unbounded.